Yeah, so in a prior life, I did physics, and before I switched to sort of machine learning. And uh, yeah, I wanted to, like I said in the email, when I was an undergraduate, I took a course called Order of Magnitude Physics, which was also called Physics 101. And honestly, it was sort of, it's the best class I've ever taken. And I feel like the course sort of gave me a audacious curiosity and a willingness to sort of like estimate things, even things that I have no right to estimate. And I have always wanted to try to sort of pass that on. And so this is my sort of attempt at doing that. I don't know if I'll do it justice, but I wanted to kind of give it a shot. So the slides you can follow along, go/Brainiversity OOM for order of magnitude. I also made a problem set, which I'll probably add a little bit to, but I would encourage people to kind of work on maybe for next week. And then also, if you haven't already, you can join the chat room for the course, where maybe we could talk about things after class and prepare for sort of next week. Because I do want things to be a little bit more open, and in particular, you know, what we're going to talk about next week, I want feedback from y'all. Okay, so like I said, the course, I don't know if I'll do justice, but to kind of summarize, I think the central tenet, there's this quote by physicist John Archibald Wheeler, never make a calculation until you already know the answer. And I feel like that's the sort of lesson here. All too often, I feel like, you know, especially like in coursework or stuff, or even in our research, I spend a tremendous amount of time kind of manipulating symbols, like getting Mathematica to provide an answer, getting code to kind of do the right thing. And I often kind of get lost. You know, I get lost. I can't see the forest for the trees and sort of don't know where I'm headed anymore. And I feel like it's always important to keep your feet on the ground and really sort of, before you engage in too much manipulation and calculation, you really want to have a sense of what you think the answer ought to be. And what we need is sort of tools in order to do that, and guidance and principles that we could use to try to help us kind of know the answer before we do any calculations. So you may have heard of like Fermi problems, right? These are kind of classic, you know, like old Google interview type questions. They're generally these, you know, seemingly impossible to know questions that you're supposed to try to estimate. And in many ways, I think that's what we're going to talk about, is sort of ways for trying to get better at these sort of things, and in particular, maybe relying on some kind of like physics knowledge and stuff like that. So, you know, classic ones include things like how many piano tuners are there in Chicago, or mass of all the automobiles scrapped in North America this month, or how much water would heat up going over the Hoover Dam. These are called Fermi problems because they're named after Enrico Fermi, a famous physicist. In fact, Enrico was famous for his ability to estimate seemingly anything, sort of off the top of his head. One of the, I think, most impressive stories is here on the right is some declassified notes from the Manhattan Project. Fermi was involved. And in particular, if we zoom in at the first Trinity test, here's Fermi's account of what happened. About 40 seconds after the explosion, he's watching from a distance. The air blast reached me. I tried to estimate its strength by dropping from about 6 feet small pieces of paper before, during, and after the passage of the blast wave. Since at the time there was no wind, I could observe very distinctly and actually measure the displacement of the pieces of paper that were in the process of falling while the blast was passing. The shift of about 2.5 meters, which at the time I estimated to correspond to a blast that would be reduced by 10,000 tons of TNT. So here we have Fermi witnessing the first ever nuclear explosion, and he sort of has the wherewithal to pick up scraps of paper and drop them before and after the blast wave goes by, notes that they go 2.5 meters back, and he's able to turn that into an estimate of the yield of the explosion. Now, this, I feel like, you know, exemplifies this spirit of being able to kind of determine an answer without really doing much work. I don't think any of us are going to be like Fermi, but we can hopefully try to stretch these same kind of muscles. Okay, so I want to emphasize that, yeah, I don't know. There are better resources than me for developing these skills, and in particular, I want to recommend these two books, Street Fighting Mathematics and The Art of Insight in Science and Engineering by Sanjay Mahayan. Both of these books are freely available, MIT Press. If you go to these are clickable. If you open the slides, it will take you to the page, but then they're open access. So if you click the open access link, they're kind of free to download. And I would encourage everyone to kind of check them out. And I'm going to be cribbing from these books for some of the examples and some of the things I'm going to tell you about. Okay, so let's zoom out. Why is any of this possible? Here's a picture. I don't know if any of you recognize this picture. There's a sort of featureless dot there. It just so happens that that dot is Earth. This is a remastered version of the pale blue dot picture, where Voyager 1, when it was 6 million kilometers away from Earth, turned around and took a final snapshot before it sort of went off into deep space. And everything that you know, all the people you've ever met, any of the things you've ever interacted with are kind of just on that pale blue dot. I feel like this picture gives me a lot of perspective. And in particular, it gives me the deep sense that nature sort of doesn't care about, there's sort of a Copernican principle, right? Nature is much bigger than us. The universe is so much bigger than us that it doesn't care about our units. It doesn't care about our coordinates. It doesn't care about the way that we describe it. And this has profound implications for the way in which the world can work. In some sense, we are just, we offer imperfect descriptions of things happening around us, and it's up to us to ensure that those descriptions don't unduly misguide us. Nature doesn't care about the words that we use to describe it, and this has profound implications. And in many ways, all I'm going to tell you about today is some of the implications of that, this consequence, this fact. So one consequence of the fact that nature doesn't care about our units is something you may or may not have heard of, Benford's law. So not actually discovered by Benford, right? But Simon Newcomb in 1881, this was before computers, pulled off his table of logarithms, off the shelf. Table is just a big book full of the logarithm of a whole bunch of different numbers that you would have to use, before calculators, and noted that the pages that if you tried to look at the logarithm for numbers that started with 1, those pages were sort of dog-eared more than the rest, suggesting that, in all of his calculations and all of his life when he was going about things, he was trying to compute the logarithm of numbers that started with 1 more than any other number. He sort of thought about this. Let's think about this. What would this mean? I mean, we know that the universe doesn't care about our choice of units. So what sort of implication does that have? Let's imagine for a second, what should the distribution of leading digits be for numbers that occur in the world? Let's imagine for a second that they're uniform. So what are we going to do? Here, up in this corner, let's imagine this equation. We'll call it the significand. All we're trying to do is, given any number, I want to sort of write it in scientific notation and forget the power of 10. I just want the sort of leading number. So something like 2,342.234 is going to become 2.342234, right? 0.00123 is going to become 1.23. So now every number that I ever look up, if I ignore the power of 10, it's just going to be between 1 and 10. Now let's imagine for a second that I have a uniform distribution for all these numbers, just hypothetically. If the distribution of numbers in my book, I collect numbers about the world, I go and take measurements, I write them all down, and they happen to be uniform, but let's say I was doing my calculations in feet. What would happen now if I switched to yards, or vice versa? If I was doing it in yards, what would happen if I were to switch to feet? If I had some distribution of numbers, here's 100,000 numbers all sort of uniformly distributed, and we're measuring their significand. If I multiplied all those numbers by 3, imagine, if you will, in a second, take all the numbers and stretch them out by a factor of 3 on the x-axis, kind of just goes out by a factor of 3. 3 goes to about 10, 10 goes to about 30. Since we've gone off the scale, if we compute the significand, it wraps around. And what we end up with is sort of 1/3 of the numbers that used to go from 1 to 3 now stretch out from 1 to 10 uniformly. And then the rest of the numbers that sort of were from 3 to 10 stretch out from 10 to 30. When we compute the significand, they get wrapped back around. So sort of 1/3 of all of our numbers are now uniform. The other 2/3 are uniform between 1 and 3. And the important thing to note is this is a different distribution than this. What does that tell us? That tells us that if we had written this book and all of our measurements were uniformly distributed in yards, they would no longer be uniformly distributed in feet. That would mean the universe would have to care whether I chose yards or feet. And the universe doesn't care. It doesn't care about my choice of units. So if there is going to be some distribution by which numbers naturally occur, that distribution has to be invariant to our choice of units. It needs to sort of survive the process if we convert between different unit systems. So let's see if we can try and find that. What would that mean? It means like it doesn't matter. If there is going to be some distribution, I could multiply it by any number and it won't change. So let's try and find it. Let's actually take this distribution and let's multiply it by a bunch of random numbers. Where are we going to get those random numbers? Why don't we draw it from this own distribution? So what I'm going to do is I'm actually going to reach into this bucket. I'm going to draw out random pairs. And I'm going to multiply random pairs of numbers together. And then I'm going to compute their significand again. I'm going to wrap it back around. If I do this once, what happens? This happens. Suddenly the numbers are, they start with more one-off when there's some kind of bias that shows up here in the leading digit of significand. Let's do it again. Now I take numbers from this bucket. I pull out random pairs and I kind of multiply them together and compute the significand again. Started going even more towards 1. Let's do it one more time, a third time. I'm going to reach into this bucket, take the numbers out, multiply them together. Oh, very little changed. It seems as though we've reached some kind of stable point, some kind of a distribution that is invariant to this operation. In fact, this distribution is very close to 1 over x. This sort of power law, this Zipfian distribution, if the digits that occur in the world have a distribution that goes like 1 over x, they sort of survive this operation. Just to convince you of that, I can take these numbers, and now I can do the thing that I started with. I'm going to take these numbers out, I'm going to multiply them by 3, I'm going to wrap it around, and we're going to go from this blue distribution to the yellow. The same distribution. This distribution is invariant to this operation. This distribution doesn't care about your choice of units.
Alex, can I ask a question?
Yeah.
Why do we only care about being invariant with respect to product when some of the measurements, for example, temperature or energy, the zero also matters, meaning that we also need to be invariant with respect to addition or something, or translation at least?
Yeah. So there are different kinds of quantities in the world, but I guess like for the most part, physical quantities, like in some sense, this is telling us that the world is for the most part multiplicative, right? Most quantities are sort of like more or less positive numbers. There's an amount of stuff. And for those kinds of quantities, the way that we change between unit systems is multiplicative. And so in so much as the universe doesn't care about our choice of unit system, it should be sort of invariant to multiplication. You're right, for things that act like displacements, like we would imagine a different sort of thing, but for things that behave like quantities or like amounts, which is arguably most of the quantities that we measure, because the way that we transform between unit systems is just to multiply, right? That's how I convert from feet to meters or meters to inches or whatever. I would need them to be invariant to under multiplication. And in many ways, the world and most of the things around us behave in this way. Multiplication is the sort of the guiding transformation.
Okay, thanks.
So if we wanted to, here we did it for all kind of continuous significance. If we really wanted to, we could like bin this thing by digits, and then you find the Benford's law that you'll see on sort of Wikipedia. If you go out and measure numbers in the world, and Benford got his name associated with it because he went and measured, I think, 20,000 numbers of various things, city populations and lengths of various railroad tracks and all kinds of stuff. They follow this distribution. Like the leading digit is 1 30% of the time, and 9 is very rare. And hopefully now you understand why. Why? Because nature doesn't care about our choice of units. And so if numbers are going to be distributed in any way, it has to be in a way that survives unit conversions. You can check all different kinds of numbers, just grabbing a couple of things from Wikipedia. If you go and reach for physical constants from NIST, they follow Benford's law. If you look for population sizes for all the countries in the CIA World Factbook, they also follow Benford's law. So there's this sort of underlying property of the world around us and the quantities that we measure where 9s are rare and 1s are common. And that's a result of the fact that the universe doesn't care about our choice of unit system. That's one implication. And what we're going to do is we're going to kind of continue to explore consequences of this phenomenon. But just to leave you with this relevant XKCD, a lonely 9 on the microwave.
Alex, a quick question.
Yeah.
So I can see why this explanation that you gave applies to things with units, like physical constants or whatever. It's not super clear that it should apply to something that is unitless, like a population. Is that?
Well, I would argue that populations are unitful, right? We measure in people, we don't measure them in fingers. Or we could measure populations in fingers just as easily we could measure it in people, right? Or heads, or feet, or left eyebrows.
I see. So you would say that there's nothing that's actually truly unitless.
Well, let's talk about that. So what is a unit? Well, what's a number? What's 4? Is 4 a lot? Well, as the meme on the internet goes, it depends on the context, right? $4 is not a lot, 4 murders is a lot. Units
Okay.
provide context. That is what they do. They allow us to make comparisons. 4 murders, $4. If I, for instance, just told you I'm 12.1 tall, what have I told you? I've told you essentially nothing. I really haven't given you any information whatsoever. I'm 12.1 tall. What does that mean? It doesn't mean anything. If I tell you instead that I'm 12.1 pixel 5s tall, now I've kind of given you complete information. I've given you some kind of context, and I've given you all the information you need to know how tall I am. Right? I've chosen a unit. I've chosen a comparison. I've chosen some kind of baseline, something that I could measure with respect to. Once I give you a unit, then you're kind of like I said, you can convert to any units you want. If you wanted to know, once I tell you I'm 12.5 pixel 5s tall, you could figure out how many millimeters tall I am, or how many feet tall I am, or how many inches tall I am, or how many Eiffel Towers tall I am. Once I provide the context, then you kind of know everything. Really, what I've told you, right, is when I provide the unit, it's as if I'm trying to communicate a dimensionless number to you. What I'm actually trying to communicate to you is a ratio. When I say I'm 12.1 pixel 5s tall, I'm telling you that my height divided by the pixel 5 height is a number, a pure number, 12.1. No dimensions, no units, no nothing. It's just a pure ratio. Dimensionless numbers are the only things that we can really ascribe size to, right? Because we argued earlier that the world is kind of inherently multiplicative in the way that it kind of handles transformations for quantities. Under multiplication, 1 is special. 1 is the multiplicative identity. It's sort of the one number that kind of sets it's the origin. 1 is nothing. It's the identity. And so in comparison to 1, for pure numbers, we have an absolute sense of big and small. 10 to the 3 is big. 1,000 is big. It's 1,000 times 1. It is 1,000 times bigger than 1 is. If I multiply by 1,000, things get 1,000 times bigger. And it sounds like this is all, but it's true, right? I'm actually reflecting something independent of units and dimensions and things. The number 1,000 is a big number compared to 1. Number 10 to the minus 4 is a small number. Compare things to 1, and I'm actually sort of saying something useful. Meanwhile, when we talk about physical quantities, they themselves aren't big or small, right? I'm 12.5 pixel 5 big or tall. Is that big? Am I big? That's sort of a nonsensical question, right? I'm big compared to an ant. I'm small compared to the sun. I'm moderately bigger than a pixel 5, right? That 12.1 is telling you, it itself is a comparison between my height and the height of a pixel 5. But my height in and of itself as a physical quantity, in the universe, doesn't really have, I independently can't describe it being big or small. So that's what units are. Units are a sense of context. They're a way to kind of give you a comparative measurement for anything that you might measure in the world. So if that's what a unit is, what is a dimension? Dimension is a way of describing different experiences we have about different kinds of measurement, right? So here's this town sign. Population 562 feet above sea level 2150, established 1951, total 4663. Why is this a joke? Why is this funny? This is funny because it's nonsense. This is not a valid operation to do. And let's try to think about why, right? Imagine I've got 2 people, Alice and Bob. They kind of going about their life. And what's one thing that we can unambiguously say that everyone in the universe has to agree to? If this is what Alice and Bob are, Bob is taller than Alice. Everybody has to agree. If Alice and Bob come upon a stick, they could use that stick as a unit, and they could start to take measurements, right? Maybe they discover that Alice is 4.7 sticks tall and Bob is 5.4 sticks tall. Now they've measured a thing, they've given it a unit, they've given some kind of context, and if they tell you that Bob could tell you, I'm 5.4 sticks tall, as long as you get your hands on his stick, you've learned everything you need to know about how tall Bob is. In fact, knowing that Alice is 4.7 sticks tall and Bob is 5.4 sticks tall, there's other things that you can do with this, right? If I lay down some sticks, I can lay down more sticks. So as long as things are sort of in the same unit, I can clearly add them together. 4.7 sticks plus 5.4 sticks is 10.1 sticks. I've made a prediction about a measurement that I could take. If Alice lays down and Bob lays down, in front of her, and I measured that in a number of sticks, I can make a prediction about what I'm going to see. It's completely valid to add sticks to sticks, right? Got sticks in this hand, sticks in this hand, stick them together, I got more sticks. We can also use this one, because I've given you the unit, I've given you the context, you can translate between different units. Like we could do something like, measure ratios between Alice and Bob. We could measure Bob in Alice's, and we could measure Alice in Bob's. There's nothing stopping us from doing that because I've given you the unit, I've given you the context, I've given you all the information. You can kind of work this out. And so it's not just that the units have to match. There's something else. A physical quantity has something else, some other nature ascribed to it that also determines whether or not it's valid to add. Because we decided I could add sticks and sticks, and that seems very natural. I got sticks in hand, sticks in hand, I can compare them. But also, I can add sticks and Alice's, right? If I have 4.7 sticks, that's a sort of height, and I know Alice's height, I should be able to add those two things together. Alice could lay down, and I could lay down 4.7 sticks on top of her, and that's still going to be a length, right? That's valid. Even though the units don't match, those things do match. I can compare Alice's and sticks. There's a dimension that's shared between them. They're both a length. There's a experience about a fact in the world, length, like things extend spatially a certain amount that these two units share in common. And because of that, I can add them together. I mean, if you want, another way that you can justify adding them together is because I can convert between them, right? I know how many sticks each Alice is. And so if I wanted to, I could take the 4.7 sticks and I could take the Alice, I could multiply by 1, written in a special way, 4.7 sticks per Alice. The Alice's cancel, and I'm left with sticks plus sticks. Sticks plus sticks is the thing I understand. I can add the 2 sticks, 9.4 sticks. Alice and sticks are sort of like apples and apples. They're both describing the same sort of experience in the world. I can add them together. They have the same dimension, even though they don't have the same unit. What's a different sort of dimension? Let's say Alice and Bob make a racetrack. They lay down some sticks. They trace out some kind of rectangle. They run across it, and they measure how fast they go. They can't measure how fast they go. There's something else. There's some other experience in the world that they need to measure, which is something like the extent of time. For that, they need some way to measure time. They need something like an hourglass. And the kind of important thing, and I don't know how, but like sticks and hourglasses are like apples and oranges. These are different things. They are different dimensions. They sort of occupy different experiences in the world that aren't comparative. What's bigger, 20 sticks or 1.2 hourglasses? Which is smaller? That's a nonsensical question. I can't convert between the two. I can't compare the two. They're different dimensions, and I can't compare them directly. Sticks and Alice's are different units. Length and time are different dimensions. They're sort of a different thing entirely. They're incommensurate. They're incompatible. I can't relate an experience of sticks to an experience of hourglasses. They're different things. So when things are different dimensions, I can't add them because I can't compare them. If I can't say that any amount of hourglasses and sticks is equal, I certainly can't add them together. I can't say one is bigger than the other or less than the other or equal to the other. So I can't add them. What can I do? Well, one thing I can do with things in different dimensions is I can multiply or divide them. Like that's valid. And that corresponds to different sort of joined experiences I have in the world. For instance, Alice and Bob might be interested in the size of their racetrack. When they made their racetrack, they laid down 5 sticks across and 20 sticks long. And they could ask, there's a different kind of experience in the world. It isn't the same as length. There's a different experience called area. The amount of paint you would need to cover it, the amount of sheets of paper you would need to cover it, the amount of tiles you would need to lay down. And that experience, we can kind of trust units as a label of dimension, and we can do arithmetic, and we can do multiplication and division. When they laid down 5 sticks across and 20 sticks long, if you multiply 5 sticks and 20 sticks, you get 100 square sticks. You get 100 sticks squared. And that's actually reflecting a different kind of process I could do in the world. I could measure the width of the track, the length of the track, and multiply those two numbers together. I could take 5 sticks times 20 sticks and get 100 sticks squared, or I can make a little square stick. Alice and Bob can make a little frame, 1 stick across, 1 stick big, and they can count how many such frames tile their track, how many such tiles would fill their track, and they would discover it's 100. So I'm allowed to multiply, in this case, a length dimension and a length dimension, and I get a different kind of dimension. I get an area. I get a different experience in the world, but like the experience is transferred. They do align because I can kind of still do conversions. I've still given you complete context. If I tell you that their track is 100 square sticks, you'd be able to figure out how many square Alice's it is, and you get the right answer. If I know that their track is 100 sticks squared, and I know that each Alice is 4.7 sticks, if I multiply by that number squared, the sticks cancel, and I figure out that their track is 4.5 square Alice's. If I made little Alice-sized frames, laid them down, it would take 4.5 of them to cover the track. I did this with a length and a length. You can do this with arbitrary dimensions because the math sort of still works out. Because the way that you convert between units is multiplicative, as long as I form arbitrary products and quotients of different dimensions, the full thing will still transform multiplicatively. It sort of stays within the valid dimension algebra. So for instance, if Alice and Bob wanted to measure a different experience in the world, a sort of rapidity, like how quickly they move across the track, they could measure that by taking, the length of their track, 20 sticks, and they could divide by how many hourglasses it takes for them to cross the track. And here too, the math, even though I want you to think a little bit, this looks like a trivial equation, but it's doing something. It's telling you something about a whole series of kind of experiments that you could do in the world, right? 20 sticks divided by 1.2 hourglasses is the length of the track divided by the number of hourglasses it takes for them to go across. But if we kind of carry through the algebra, that becomes 16.7 sticks per hourglass. That's a different sort of thing, right? That's a different sort of measurement that you might do in the world. A stick per hourglass. You could imagine building a machine that moves 1 stick every time the hourglass turns over. And then I could you could compare the relative speed of that apparatus to the speed at which Alice or Bob crossed the racetrack. And that's sort of what's happening under the covers here. So and I realize that was all kind of like philosophical and stuff, but I'm telling you stuff that you sort of already know, but I wanted you to kind of take a few minutes to try to engage and think deeply about what's happening here. So why is this sign so humorous? It's because it's impossible. It's asking, apples and oranges. It's asking to compare things that can't be compared. Okay. With all that out of the way, the universe doesn't care about our choice of units, doesn't care about our choice of coordinates, and this has profound implications. One implication we saw was that numbers themselves are sort of distributed uniformly. Another consequence is, like we just discovered, there's a certain algebra corresponding to units and dimensions. There's a certain algebra that physical quantities have to respect. Namely, you can't add 2 things that are of different dimension. And this has profound implications for the types of formula that I'm allowed to write down. And dimensional analysis is the sort of working through, kind of turning that crank, given some set of physical quantities, what are you and are you not allowed to write down? And it turns out the fact that the universe doesn't care about our units, that implication means that the space of all possible formulas you can form is much smaller than you might otherwise expect. So if you remember, Fermi was able to determine the strength of the atomic bomb by dropping a piece of paper. We don't have any paper. We don't get to experience what Fermi experienced, but we can do something else. So at the time the Trinity explosion took place, it was highly classified, but Life magazine published a series of a few photographs that showed the fireball from the first test. Here's one of the pictures on the right, very conveniently trying to give you a sense of the scales involved here. Here's a length scale, and here's the sort of time after the explosion. And even though what we're going to do here isn't the same, and it's very simplified, here's G.I. Taylor. G.I. Taylor, a British physicist, was actually able to work out the strength of the explosion given access to just these kind of figures. And we're going to do it too. We, even though we might not know physics or anything, we are going to be able to estimate the strength of this atomic blast, sort of just using this picture and the fact that the universe doesn't care about our units. Okay, so how is this going to work? This is going to work because if there is, like, we believe that there's some formula out there in the world that relates these quantities with each other. We are determining the strength of the atomic bomb. That's going to be like an energy. We are given a time on this photograph after the explosion. We're also given the sort of radius, or a length associated with the size of the fireball. And we know that this fireball is happening in air rather than like in water. And that's got to be important. That's got to sort of drive the physics. And so the way that we can kind of capture the fact that it's air is we need to measure some physical quantity associated with the air. And here we'll use the density, how heavy air is as a substance. Now, the thing is that, if, whatever, physics has laws, and those laws have to govern, they have to give us some function, some relationship between these four quantities. There has to, somewhere out there, be a formula that, let's say you were smart, you got a physics PhD, you do some kind of calculations, you could imagine doing all kinds of differential equations, doing some kind of crazy simulation. There's going to be a formula that you could write down that relates these four physical quantities in some way. And you could imagine that in general, there's some function. That function has to equal 0, because let's say you had a function that equals some constant, you could subtract the constant, you could write it in this form. But we know sort of more than that. We know that the world is kind, the world is sort of simple, the world is smooth. We don't have to worry about crazy discontinuities or these devil staircases type things. I mean, in general, the world is kind of continuous and nice. So any function that we encounter in physics, we sort of believe we could write as a Taylor expansion. It's ultimately some kind of polynomial, right? Maybe it's some nonlinear function like an exponential or a sine, but even those, I can like Taylor expand them and I can write them as just some kind of big polynomial. So whatever this function is, whatever this relationship between these four physical quantities, I've got to be able to write it as some kind of big generalized polynomial. Whole bunch of terms, some of which are going to appear, and those terms I could write as just powers, relative powers of E and T and R and rho with different coefficients. But we know that because the world doesn't care about our units, we can only add things that have the same dimension. Whatever this kind of crazy polynomial is, each of the terms have to have the same dimension. And in particular, that means that if I imagine writing this thing out, I could grab any one of those terms, and I could divide every term in the equation. I could divide both sides of the equation by that term, and I would end up with a new sort of polynomial. But now the one term that I took and divided out has to be 1. It has to be dimensionless, right? I've done a comparison of two dimensions that are exactly the same by taking a number and dividing by itself. That's a pure number. All the rest of the terms, their powers change, their coefficients change. Now I've got a ratio in there. But now all of those terms that are left have to themselves also be dimensionless. Because I can't add 6 and 7. I can only add 7 and 8. All of these things now have to be dimensionless combinations. So what we can do is we can look for combinations of these physical quantities, powers, relative powers of these four terms that we could combine and make dimensionless things. Because we know that those are the only things that are going to be allowed to appear in this big formula, whatever it is. So let's look. For that, we need to know what the dimensions of these quantities are. So we have a time. That's an experience of time. We'll give it's a time dimension. You measure that with clocks. We had a size. That's a length dimension. We measure that with rulers. We have the density of air, which is a sort of a density. It's an amount of substance in some space. I build a box, and a box is so big, and I put air in it. It weighs so much. So the dimensions there are sort of a mass per volume, a mass per length cubed. And finally, I have an energy. And you might not know or remember the dimensions of energy, but the kind of neat trick here is, because all formulas in physics have to be dimensionally consistent. If you can remember any formula whatsoever from anywhere in your life about how to make it from anything else, you could kind of figure out, again, like I don't remember what the dimensions of energy are, but if I need to remember, I do remember that E equals mc squared. That was something somebody told me once. And I know what the dimensions of mass are. They're a mass. And I know what the dimensions of C are. C is the speed of light. It's a speed. That's a length per time. So the dimensions of energy is a mass length time per length squared per time squared. And so the formula that relates these four quantities can only involve these dimensionless factors. Let's try to make one. So let's just kind of start doing it. I'm going to write down an E. The dimensions of E are mass length squared per time squared. And I want to make this thing dimensionless. I got everything to cancel out. So let's start with the mass part. I need the mass to go away. How am I going to make the mass go away? Well, the only other one of these quantities that has a mass is the density. I'm going to divide by it. I'm going to take the energy, I'm going to divide by the density. The masses are going to cancel. I had an L squared over T squared. I divide by a mass per length time, and now I have a length to the fifth squared. And now I need those to go away. How do I make those go away? Well, over here I've got an R, that's a length. So I could use that to get rid of the L to the fifth by dividing by R to the fifth. And I need to get rid of 2 powers of T, so I could take T squared. And if I wanted to, I could form this combination. This is a dimensionless factor, has no dimensions because they've all canceled out. This is a pure number. This is just a number you could measure in the world. It has no dimensions anymore. The 12.1, it's the ratio of like my height to pixel 5's height. This is a pure number. So we know that, you know, if some formula exists in the world that has to relate these 4 quantities, it has to be written as, instead, a formula of dimensionless combinations. And we found one of them. We found one dimensionless combination. Are there any others? How could we know? And so here, there's a neat, I mean, in our case, it felt pretty clear that this was the only sort of choice that we had. I mean, I guess I could take this whole thing and I could raise it to the 2nd power. I could square it, or I could cube it, or I could take it to the 4th. But that's not independent, right? We were imagining an arbitrary nonlinear function of this thing, and so I could wrap all of that up into the function, and I don't need to consider other powers of this one thing. Are there sort of other independent combinations I can form? It seemed like there wasn't, but you can actually kind of make this kind of form. Like, how would you describe the algebra of what's happening in the system? It is like a linear algebra system. If you think about forming a combination of these 4 quantities, e to the alpha, t to the beta, r to the gamma, rho to the delta, what is the dimension of this vector? If I give you the 4 numbers, it has a dimension, and we can actually, like, it's a linear algebra system that determines what the dimension is. If I had an alpha, beta, gamma, delta, I could write out these 4 quantities, and I express them in kind of 3 independent base dimensions. An energy was a mass length squared per time. A time was a time. You know, radius was a length, and density was a mass per length cubed. Given any vector here, if I multiply this matrix times that vector, it's going to give me a vector of the powers of the dimension of the resulting product. And once we imagine this thing as this linear algebra system, then this question we had, like how many different dimensionless combinations form, is like a linear algebra question. It's a question of how, like strictly speaking, is the question of what is the null space? What's the dimension of the null space of this matrix? And I don't know, you know, if I have a 4x3 matrix that is made up of non-degenerate rows, the null space has to be 4 minus 3. It has to be 1 dimension. And that is the content of the Buckingham pi theorem. Buckingham pi theorem is just a name for a thing applied to dimensional analysis, which is telling you that if you have n physical quantities measured in k independent dimensions, there are n minus k independent dimensionless constants. It really is just a statement of this kind of linear algebra thing. If you imagine I have an n by k matrix, and the rows are non-degenerate, then the null space has to be n minus k dimension. So in our case, we had 4 physical quantities measured in 3 fundamental dimensions, mass, length, time. 4 minus 3 is 1, and we found one, and that's the only one. Any other dimensionless ratio that you would form has to be sort of products or powers or roots of this one thing. And so we know that whatever equation there was that related these 4 quantities has to be some nonlinear function, potentially, of this pi 1 has to equal 0. Maybe it's exponential, maybe it's logarithm, maybe it's sine, maybe it's some arbitrarily crazy kind of polynomial, but still there's only one argument. And so if that's the case, if there's some function of pi 1 equals 0, I can like invert this, right? And it tells me that whatever this kind of function is, I mean, physics, again, the world is kind and functions are always invertible. Pi 1 is just going to be the inverse of like 0 of this function. That's just going to be some constant. Again, this thing is dimensionless. It's just going to be a number. It's going to be a pure number. And so we know that the only way that these 4 quantities can be related in a world, in a universe that doesn't care about our choice of units, is that that formula has to be written only as a function of pi 1. And so any function of pi 1 I could kind of invert, and I could write like this. Pi equals a constant. The last thing that happens, and this is somewhat magical, is the universe when you find formulas like this, when there are physical equations that are, when there are dimensionless constants, like we said, the world is sort of multiplicative. The only number that's special is 1. And so it so happens that constants, dimensionless constants that show up in physics formulas tend to be about 1. They tend not to be very big or very small, because very big or very small things need explanation. And there's no explanation left once you remove all the units. So they tend not to be 10 to the minus 6 or 10 to the 6 or 10 to the 4, 10 to the minus 4. Maybe they're 10, maybe they're 1 over 10, but they're generally around 1. They're usually about 1 order of magnitude away from 1, because they don't really have a good reason not to be. So in this case, we can actually just estimate. If we're okay with being only within a factor of a few of the answer, we can say that we don't know what C is, but it's not going to be much more than a factor of a few, either up or down. And so let's solve this equation. Then we get E goes as rho r to the 5th over T squared, and we just plug in some numbers. Density of air, 1 kilogram per meter cubed. Well, what's the radius of this thing? Oh, they gave us this bar. It's about 100 meters across. Take that to the 5th. What's the time at this with this took place? 0.016 seconds. We can do this. We can do some math. Just kind of estimate this stuff. This is 10 to the 2 to the 5 is 10 to the 10. We got 1 kilogram per meter cubed. The meter cube is going to cancel the meter to the 5th and 2nd. The whole thing is going to be in SI, so it's going to be energy. It's going to be a joule. We do this whole thing out. We get 10 to the 10 upstairs. We get 1.6 10 to the minus 2 squared. 10 to the minus 2 is going to be 10 to the minus 4. 1.6 squared is going to give me something like 2.5. I could pull out a power 10, 10 over 2 and then 10 and a half, and I get about 10. Well, I get 4 10 to the 13 joules as the unit in SI. And if I wanted to compare it to something that we may have heard of, we could compare this to kiloton of TNT energy equivalent. Yeah. Ibrahim said the fine structure count is 1 over 137, and that's kind of 2 orders of magnitude away from 1. And that's fair, but that's fair. We'll actually talk about that later, or there's a thing on your homework to look at the fine structure. Okay, let's convert units here. Once we've given the context, we've worked everything out. 4 10 to the 13 joules. If we look up, we could look up kiloton TNT energy equivalent and work out that this is about 10 kilotons of TNT. What was the actual Trinity test? It was about 25 kilotons of TNT. We just looked at this picture and we said the universe doesn't care about our units. That was enough to work out that if there was any relation whatsoever up to a multiplicative constant that's a pure dimensionless number that we didn't know, we could figure out that the answer had to be about 10 kilotons of TNT equivalent. Real answer was 225. That tells us that the unknown number that we didn't know was 2.5, close to 1. That is the power of dimensional analysis. Yes.
Yes, like very, very interesting. One question I didn't understand where we use the first thing that the nature doesn't care about the numbers. I mean, clearly see where the dimensionless thing we use to try and kind of calculate this. Is that by making C close to 1? Is that how we kind of use that first fact?
So it went into the consequence was that if the universe doesn't care about our units, then we're only allowed to add things of the same dimension.
Okay.
And because we're only allowed to add things of the same dimension, the formula couldn't be arbitrary. It had to be dimensionally homogeneous. Whatever the formula was, all of the terms had to have the same dimension. And that imposed a lot of structure on the possible form that the equation could take. And we discovered that in our case, with 4 variables in 3 dimensions, there was only one combination that we could form.
Got it.
And since there was only one combination, we got it up to a single dimensionless constant. In our case, that was 2.5. And so we were able to kind of get the answer as close as we can kind of a priori guess what dimensionless constants are in the universe. And I'm telling you, by experience, these tend to be within an order of magnitude or so. These undetermined constants tend to be between 0.1 and 10-ish. In this case, it was 2.5. But still, like, the point was we got a heck of a lot closer than I think we thought we could have beforehand. If I asked you to guess how big the explosion was, the fact that you could get it within a factor of 2.5, just given this photograph, is sort of the remarkable thing. There wasn't anything that went into that except the requirement that whatever the formula is, it has to be dimensionally homogeneous.
Cool, thanks.
Yeah. Vinay, it might be worth having another one closer. Yes.
Also had a
So,
question.
yes.
So we said at the beginning that there must be these 4 quantities that have to relate to each other so we can compute the energy. But there could be many more, right? Like
Yes.
how did we know
So
that
let's-
it's these four?
Let's talk about that. So that's where, yeah, let's talk about that. So fantastic question. Let's dive in. Okay, so actually at this point, I think we're kind of 45 minutes in. I definitely want to talk about that more. That's what we're going to go next. We're going to talk about, like Vinay said, I mean, part of, as you practice this, you get better at it. Part of the art of dimensional analysis is knowing what factors you should or shouldn't include, but it isn't that sour. And what I'm going to show you is that even the analysis itself, the value that these numbers actually take can guide you and demonstrate to you, or you could use to estimate how wrong you might be for either including or not including certain factors. That's what we're going to talk about next. I thought I did want to take like a little bit of a break. It's been sort of 45 minutes. So why don't we kind of take a couple questions or a couple minutes, people can kind of get up, walk, stretch their legs. I'll answer sort of other questions. This is sort of a natural, let's take a short break. So let's say by 12:55, 50, yeah, we'll say 12:55. So it's in 7 minutes, we'll kind of pick up again. I'm going to hang out here if people have questions. What's coming up next is we're going to kind of really sort of dive in and try to answer this question. How do we know what things that we do and don't include? What happens if we include too many? What happens if we include too few? And keep going from there. So I'm going to stretch my legs. I'll be right back. But yeah, feel free to ask questions. So for anyone who's, yeah, if anyone has questions, I'm happy, we'll wait a few minutes, but for people who are still here and listening, I'd like you to take a look at this. And the question is, what's wrong with this? This is how, you know, a question might be written in a physics textbook, but it's bad. And why is it bad?
Alex, I had one question.
Yeah.
So we established that you were talking of this theorem where there are n independent variables and k equations essentially, and that means that null spaces of dimensional k and minus k. How did we use that? Yeah, that Buckingham Pi theorem. But before that,
yeah,
you wrote down a form. So you guessed the variables. That's okay, which enter the equation, and then you wrote down a form. You basically seem to use this theorem to write down the possible structure of the formula. So can you like tell me how did you conclude the possible structures of the formula given the variables that might enter the equation.
Yeah. So okay. So what I was using the formula for was trying to convince me that once we found one dimensionless constant, we were done. Like there was only one. So we're going to do a bunch of examples to come, and we'll see. But what it tells, what we use the Buckingham pi theorem to tell us is how many independent dimensionless constants exist.
Okay.
And then once we find those, we know that the formula has to be just in terms of those. In our case, we got kind of lucky in the sense that the total number of dimensionless constants that could exist was 1. And so once we find 1, we know we're done, and the formula actually is like entirely solved up to a constant.
Okay.
There's no
Okay.
there's no missing structure. So
Okay. And if there were 2 dimensionless constants, then
that's exactly what we're going to do
okay.
right next. But if there were, I guess because you asked, if there were 2 dimensionless constants, then all we're going to be able to say is that there's some function that relates to 2. We might be able to solve for one in terms of the other, but we're going to be left with an entire dimensionless constant that we won't be able to determine from dimensional analysis alone.
Oh, I see. Okay. Okay. Nice.
The power comes from the fact that if we didn't know any of this before we went in, there were kind of we'll talk about it.
So one more question.
Okay.
Sorry, Panak asked a question, so I'll let him go.
Yeah, I have like a really naive question. The naive question is like, can it ever happen that there are less quantities than the number of independent dimensions?
Well, I mean, in the sense that, let's say we didn't know that we needed to include the air density. If we started with just energy, time, and radius, then we would discover that we'd have 3 equations in 3 dimensions, and so there'd be 0 dimensionless constants. And that's a big slap in the face that you're forgetting something. Like there is another physical quantity that has to be there in order to govern the relationship, because the universe is telling you that those 3 things cannot be related to one another unless there's another experiment that had to have been done. There has to be a missing physical quantity.
Yep. Cool. Yeah. That's what I was hoping for over there. Thanks.
Yeah. Okay. So I think the time I allotted has expired. I guess Robbie had another question. Quick, or was it?
How did we conclude that there was just one dimensionless constant? There was 4 quantities.
There were 4 quantities, but they were measured in this case, we measured them in 3 dimensions: mass, length, and time. And 4 minus 3 is 1. So
okay. I see. Okay.
That's the fact that we had 4 quantities, but we had 3 dimensions. The 4 minus 3 is 1. Okay. So we're going to kind of do the same thing again. We're going to try to get some more understanding of some of these things that people had asked. But let me start by this. So this is how you might read a physics question in like a physics textbook. And I think that this is terrible. And why is it terrible? Because, if it asks, a ball is initially at rest, falls from a height of h feet, and hits the ground at the speed of v feet per second, find v assuming the gravitation of g feet per second squared, and neglecting air resistance. Why is this bad? Does anyone want to? Doesn't know the answer. Jonas.
I'm gonna guess because the G doesn't require a unit, so you should ask for the physical thing and not for the value before the unit.
Yeah, that's perfect. Because if they ask the question this way, what is G? G is a number. What is V? V is a number. What is H? H is a number. What would is dimensional analysis going to give us any sort of structural constraints on 3 dimensionless numbers? If I've got 3 quantities in 0 dimensions, how many constants can I form? 3. Tell me nothing. There's nothing I could do. They've robbed me of all the structure that I could rely on by writing it this way. If instead they wrote it like this, it's sort of like, it's more accurate. It's more of what the way the world works. A ball initially at rest falls from a height of h. What is h? H is a height. It is a height. It is an experience of spatial extent. It hits the ground at a speed v. What is a v? V is a speed. If they do this, now I can actually sort of do dimensional analysis. I can actually use the way the world works and how speeds relate to distances and times in order to figure out what the answer has to be. So that's what we're going to do. You drop a thing from some height, it hits the ground, how fast is it going? And let's just figure it out. Let's figure it out with dimensional analysis. We've got 3 quantities: height, velocity, and acceleration due to gravity. So what are the dimensions of these things? Height is a length. Velocity is a velocity. It's a speed. It's a length per time, right? I go so far in so much time. And what's an acceleration? Acceleration is a velocity per time. It's an acceleration. It's how far I go, per second per second. So I've got 3 physical quantities. Now, how many independent dimensions do I have? Only 2. I've got spatial extent and I've got temporal extent. Length and time, 3 minus 2 is 1. There should only be a single dimensionless constant, and that should govern the entire physics. So what is it? I can kind of just do it by eye again. Let's look at it. If I wanted to find a dimensionless constant here, I might do something like, I'm interested in the velocity. So I'll take the velocity. The velocity is a length per time. If I want to get rid of those times, the g has times that I could get rid of, but those are squared. So what I'm actually going to do is square the velocity. I'll take velocity squared and divide by g. Oh, and then I've got kind of a length in there. I get rid of that, and I can do this. My dimensionless constant is v squared over gh. And just as before, since there's only a single dimensionless constant, the entire equation governing the relationship in these 3 physical quantities has to be just this equation equals some constant. I don't know what that constant is, but maybe I don't care. I can still say that v is up to a dimensionless constant equal to square root gh. And I've sort of gotten all the physics for free. I've got all the functional dependencies for free. I don't have to worry about anything except potentially a factor. For our problem, this tells us that if let's say I drop a ball in Earth's gravity, Earth's gravitational acceleration is like 10 meters per second squared. If I drop it from about 5 feet, like shoulder height, you kind of approximate the math, you work it out, it goes about 4 meters per second when it hits the ground, or about 8 miles an hour. And I can determine that sort of, again, for free. I didn't have to do any physics. All of it was sort of determined just by a relationship between lengths and times and accelerations and speeds. There was no freedom left in the equation. But what if I included other variables? Like we started with just the height, the velocity, and the gravity. What if the problem also said, and the ball has a radius r? Now what happens? Well, okay, what happens? I write down this physical quantity of radius. Now I've got 4 physical quantities, still in only 2 dimensions. 4 minus 2 is 2. There's an independent dimensionless constant that I could form. I've still got the one that I had before, v squared over gh, but now I can form at least one new one, independent of the first. And here's one way that I could write it, right? R over h. That's also dimensionless. Length divided by length, that's a pure number. So now, dimensional analysis sort of doesn't give me the entire answer. It tells me that if there's a relationship in these 4 physical quantities, I have to be able to write it as a function of pi1 and pi2 equals some constant. If I wanted to, I could solve that as pi1 equals some function of pi2. I could say that v is equal to square root times some function of the ratio of the radius to the height. And at this point, dimensional analysis is done. This is all it can give me. And this might feel like a failure, but I want to emphasize how much of a success this is. Imagine you didn't do the dimensional analysis. And let's say I just, set you in some kind of like laboratory, and I told you, figure out the relationship between heights, velocities, the strength of gravity, and the size of the ball. And I gave you those 4 quantities. If, imagine we're almost doing like a hyperparameter search or something, you'd start randomly choosing, you'd probably go about it by randomly perturbing all 4 of those variables. It's kind of hard to change Earth's gravity, but you try anyway. And you change all 4 of those variables, and you try to look for a relationship between all 4 variables, some 4-dimensional function. And you'd have a terrible time. However, because those are 4 physical quantities, and the universe doesn't care about our units, all of the relationships that's allowed between these 4 quantities has to take this form. And there's only a single dimensionless function that we ever need to determine. So now you could replace what feels like a hyperparameter search over 4 dimensions with now just determining a single dimensionless function. I might only need to do like 30 experiments and draw a curve, and I'm completely done, and I've determined the entire relationship between these 4 quantities.
Alex, I have a question.
Yeah.
I sometimes get confused by 2 notions here that you're talking about. One is unit and the other one is dimension.
Yeah.
My understanding is that the fact that we can only add quantities that have the same dimension imposes that, like, we get formulas like it. But the fact that the universe doesn't care about the units doesn't contribute to these conclusions.
So I apologize. I'm probably speaking too loosely and colloquially. I think your understanding of units and dimension is correct. I guess I do feel like the fact that the universe doesn't care about our units does lead to the conclusion that we can only add things of the same dimension. In the sense that Otherwise, if you try to add things with different dimensions, that quantity can't transform between units. And so if the universe, in the same way that we sort of did with Benford's law, you could imagine trying to add two things with different dimensions and then change the units. And you can't do that in a way that makes the thing invariant to changes of units. So that's sort of like, it's verboten, it's not allowed. In the same way that we wouldn't allow ourselves to imagine a world in which the numbers in the book are uniformly distributed and they're significant, because in such a world, under unit changes, it doesn't stay the same. In the same way that if we try to add things with different dimensions, if we change the units, that sort of doesn't transform homogenously, so it's not allowed.
But you even gave an example that we could apply like algebraic operations like addition, multiplication, division to quantities that have the same dimension but different units.
Yeah, the same dimension but different units, because there, by changing units, the whole equation stays homogeneous. But once we tried to add two things with different dimensions, we couldn't. I mean, invite you to kind of write out a thing where you take like your height plus your weight and try to transform it, and it won't transform. The whole equation won't transform as just multiplying by a factor. So that equation doesn't make sense. It's not allowed in the sense that the only sense in which anything you write down where you added your weight and your height is only going to work in a specific unit system. It wouldn't work. It wouldn't keep its functional form in any other unit system. Like if you tried to switch. I mean, and people do this all the time. You know, like BMI as a formula only works in a single. I think it makes this mistake. It's tied to a certain unit system, but it's not universal. And
Thanks. And one more quick question. You mentioned that in physics, usually when people see dimensionless constants, they assume that it's around 1. And I've actually heard that in other presentations and sources as well. But one thing that I don't understand is when we are allowed to change the units and do addition and multiplication, division, even when the units are different, then how are we guaranteed that? Because we can change that number by changing the unit in the numerator and not changing it in the denominator.
But that's not so the dimensionless factor. You can't change the dimensionless factor, right? I can take my height in millimeters. If I take my height in millimeters and I divide by some other height in inches, that's a pure number, and it doesn't matter what. Like the numbers in the numerator and denominator can change as I change the units of the numerator and denominator.
Yes.
But if I kind of carry it fully out and I convert this, then I'm left with a pure number, and that number is invariant to the choice of units.
Not if the units in the numerator and denominators are different. I still get a dimensionless number, but it's not 1, right? I can divide my height by my height in different units. I get a dimensionless number, which is not 1.
But if you change units of some quantity, you have to change units of all the quantities.
Yeah.
That are being measured in that thing.
When we said here that like, if Alice or Bob is 15% tall, and that is a statement that I can say that is true, that is always true. It doesn't matter how you measure Alice. It doesn't matter how you measure Bob. The state of the world is that Bob is 15% taller than Alice, 1.15 times. That is dimensionless, and that is true irrespective of how you measure. You can measure Bob in sticks, you can measure him in fish, you can measure him in feet, you can measure him in inches, you can measure him in miles.
Yeah.
But Bob is always taller than Alice.
Yeah. What is the dimension of 1 inch divided by 1 centimeter?
Dimensionless, but you have to, 1 inch is about 2.5 centimeters.
Yeah.
Right? So that's the thing, that 1 inch divided by 1 centimeter is like 2.5, and it's always 2.5. It's a number. In the same way that Bob is always 15% taller than Alice, an inch is always 2.5 times a centimeter. Right? 2.3, whatever it is. And that's just like a state of the world. Those two sticks, you make a centimeter stick, you make an inch stick. The inch stick is more than twice the centimeter stick. That's a fact of the world.
Thanks.
Okay, so we just saw something seemingly go wrong. Dimensional analysis didn't give us the full answer, but it still got us most of the answer. It told us almost the entire relationship between I think the numerator FC about one. Yes, yes. Okay, what do we do? At this point, dimensional analysis is like done and can't actually help us. But I want to emphasize that there's still more that we can often do. Because whatever this function is, like we said before, physics functions are, you can kind of Taylor expand them, just sort of polynomials. So whatever this function of this ratio is, it's going to look like some kind of polynomial. Coefficient plus a coefficient times 1 power plus coefficient times it to the 2nd power, it squared, it cubed, etc. And if it so happens that this ratio is either very big or very small, if it's very big, we could write it as 1 over it and get it written as it being very small. If this number is very small, then this like Taylor expansion, all the higher order terms don't matter. And the leading order term is just going to be sort of linear in this thing. That's just kind of like the way things are, right? For our actual problem, if I had like a racquetball and I dropped it from my shoulder height, the racquetball is about 1 inch in radius and I'm dropping it from about 5 feet. So the racquetball is about 2% of the height, right? That's a dimensionless factor, 1/50th of the height that it's dropping. And 1/50th is a moderately small number. So this ratio, R over H, for the problem I'm interested in, is 2%. It's a relatively small number, 0.02. If 0.02 is a small number, 0.02 squared is doesn't matter. 0.02 cubed is a much, much smaller number. I don't care. And so even though I don't know what alpha naught or alpha 1 is, again, in so much as dimensionless constants that I don't know about are probably close to 1, and if I only want an answer within a factor of a few anyway, even though I don't know what this function is, I know that if this ratio is small, I can estimate the effect that it will have on the answer. The fractional change in my answer is just going to order this dimensionless constant, if the dimensional constant is small. Because if the dimensional constant is small, whatever this nonlinear function is, just its linear term is going to dominate, and if it's just its linear term is going to dominate, then the fractional change in the answer is just given by the number itself. So what this is telling me is the first time we did the problem, I ignored the radius of the ball. What this is telling me is if I didn't ignore the radius of the ball, there's a missing whole function. Dimensional analysis can't tell me what that function is, but even though it can't tell me what it is, the fact that that ratio, the ball is only about 2% of how far I'm going to drop the racquetball, this is only going to affect my answer by about 2%. And I get to decide whether I care or not. Do I need the answer to better within 2% or not? I mean, then I really need to go back and determine that missing constant that I never determined, which was square root 2 in our case. But if I don't care about the answer within 2%, I'm kind of entirely right to ignore the size of the ball. Oh, also, I didn't say it, but why does this actually matter? Like what's the physics reason why you care about what the radius of the ball is in terms of the speed of what it is when it hits the ground? The answer is because if the ball is so big, it hits the ground sooner, right? If we're talking about the wave specified problem, if we specify the height above the ground, normally we're talking about the height to the center of mass, and if it goes and hits the ground, it hits the ground when the bottom part of the ball hits the ground. So there is going to be in the actual relationship in this quantity for the velocity that we would observe for the ball when it hits the ground, the radius of the ball does matter because it affects when it hits the ground. And we can actually kind of work out, if we actually kind of work that out, we discover that this missing dimensionless function that we couldn't determine, dimensional analysis couldn't determine, if we do a little algebra, turns out to be square root of 1 minus r over h. And before we even knew what that function was, we sort of estimated that because r over h was about 2%, this should only affect our answer about 2%. If we actually work it out and we crank the math, the actual fractional change in our answer is minus 0.1%, 0.08%. And this is, I think, the second order sort of dimensional analysis, and the thing that I want to communicate is even if you sort of don't know which physical constants to throw in there, the dimensionless ratios that you form, if they're very big or very small, don't matter. And you can kind of estimate the degree to which they do or don't matter. So let's keep going. I added the radius of the ball. What if I worry about the mass of the ball, right? Masses matter in physics. They show up. So what happens there? Well, now if I include mass is a different dimension, right? That's a quantity of stuff. That's an amount of material. And so now that has mass. So now how does my Buckingham Pi calculus go? I went up to 5 dimensionless quantities, but my dimensions went from 2 to 3. 5 minus 3 is still 2. And Buckingham Pi, dimensional analysis is telling me that the velocity of the ball when it hits the ground can't depend on the mass. It cannot depend on the mass if these are the only sort of things I'm willing to consider dependence on. It is independent of the mass. And I'm still left with just these 2 dimensionless constants. If I do want the mass to matter, the dimensional analysis is telling me that I need to include another physical quantity that involves mass. Does anyone have a suggestion of what we might include if we wanted to keep going? Something that includes mass? Density of air, right? Like we saw with the bomb. Maybe air resistance we heard about, right? Well, it's going to get complicated to do the entire physics, but we can still estimate how much air resistance matters. Because we can do this. We add the density of air. Now we've got 6 minus 3. There are 3 dimensionless constants. We can form a new one. And if we form that new dimensionless constant, we plug in some numbers, 1 kilogram per meter cubed, about a 1-inch ball squared. I drop it from 5 height. I divide by the mass of a ball, 70 grams for a racquetball. This again is about 2%. And so again, without doing any calculus, without doing anything, I can estimate that how important is air resistance for dropping a racquetball from my shoulder height? It's about 2% important. Maybe I don't care about 2%. That's up to me to decide. The next thing, though, I wrote this in a particular way. And notice that I wrote this as rho r squared h over m. There's lots of other ways I could have written it, right? I could have written it as rho r cubed over m. That's also dimensionless, has the same dimensions. That's what this notion of independent in the Buckingham Pi theorem goes. I could have written like that, and that would be fine. That would be an independent dimension compared to the others. But you'll notice that this is this times this, and this was our other pi. This was pi 2. So there is freedom in how I write these quantities. That freedom just means that we take dimensionless numbers and multiply or divide them by each other. But part of the art of dimensional analysis is kind of, and the way that you can most trust this like error analysis that we're doing is if you choose reasonable combinations or reasonable factorizations of these things. And for that, we need to kind of actually do a little bit more reasoning. We need to kind of think about the problem and not just push the symbols around. Somebody asked a question.
Yeah, so I have a question. So
yeah,
what if we also included something like the density of the ball instead of just the density of the air? Like,
so
in that case, you would have more variables to work with, but the same number of independent variables, right?
So let's say we added to this list, if we made this rho sub air and we added rho sub ball, because then there'd be rho sub ball, but then there'd also be the mass of the ball and the radius of the ball. And yeah, there'd be a new dimensionless constant, but one way I could choose to express that dimensionless constant would be the density of the ball divided by the mass divided by the thing cubed. And that's going to be a thing of order 1, but it's clear that so on the one sense, it feels like that shouldn't matter, right? Why, like the density of the ball shouldn't matter in comparison to the mass and the radius, but it can. And like the actual physics, like it will govern the interaction in a that has to do with the shape of the ball, right? The difference between mass divided by radius cubed and the density, the difference, like the degree to which those aren't 1, right? If it's a sphere, that's 4/3. And if it's a block, then that might be 1. And if it's a pear-shaped thing, it's going to be, whatever, 1.7. So that dimensionless factor is going to be some way of encoding the shape of the ball. And shapes of balls do matter. Different shaped balls fall different ways through the air, right? A feather-shaped ball, if I had a really extended ball, falls differently than a ball-shaped ball, which falls differently than a block-shaped ball. How differently, we could estimate by the actual size or the dependence of this variable. So, okay. So what I want to say is dimensional analysis is great, and I think it can really do more than it ordinarily gets credit for, because we could also use it to estimate how important things that we didn't consider are, or we could easily estimate the contribution of different terms by looking at the actual values that these dimensionless things take. But still, there is a sort of art. There is a sort of way in which dimensional analysis can mislead you, because it can't tell you the right combinations, the right factorizations to apply. For that, you need a little bit more. And here's just another relevant XKCD showing you, taking too seriously dimensional analysis is a little too silly. Here he discovers that Planck energy divided by pressure at the Earth's core times the Prius combined EPA gas mileage divided by the minimum width of the English Channel is a dimensionless constant. All the dimensions cancel, and you get something about pi. But then if you were a little bit too serious, you might then think that this is some law of nature. And so if the better Prius, England would have to move out to sea. And that's probably not true. So we need to do something a little bit more. And for that, we need to actually think. But what's really nice is dimensional analysis and thinking, I think, reinforce one another. And the more that you sort of do dimensional analysis and the more that you think about the dimensional analysis, the better you become at thinking, and the better you become at thinking, the better you become at dimensional analysis. What do I mean by that? Why did I choose this combination? I choose this combination because I can think about it, because it turns out to be something that I can reason about that makes sense for me. If I write it as rho r squared h divided by m, then I can interpret that dimensionless constant. I can interpret that as m is the mass of the thing, the mass of my ball, and what's rho r squared h? Why did I do rho r squared h versus rho r cubed? Because rho r squared h is a mass. It's a mass of air displaced by my ball. If I drop a thing with some cross-sectional area through the air of depth h, it's like I trace out a cylinder. And that cylinder has an area that goes like r squared, and it has a length of something like h. Rho r squared h is the sort of total mass traced out by the ball, mass of air traced out by the ball as it falls. And so I can make sense of this. This tells me a story. When is air resistance important? Air resistance is important when a thing pushes air out of the way that weighs about the same as itself. And that makes perfect sense. We can actually, I think, really lean on this and do this sort of thinking in all different kinds of ways. And this is, Sanjoy calls this twiddle analysis. What's a twiddle? This is a twiddle. When you write a twiddle b, you mean that a and b are the same up to a constant. But instead of thinking at the level of dimensional analysis, you should really think about the physics. But you don't have to get all the constants right. And that kind of really frees you up to kind of think more clearly and see the physics. So what's the sort of twiddle analysis? If I asked you to think about when air resistance is going to be important, one way you might think about it is, oh, air resistance, like its importance, I need a dimensionless constant. One thing that you should sort of always start with is looking at energy ratios. It's going to be important when the energy that goes into the air is going to be comparable to the energy of my object. And this is where hopefully you remember a little bit from physics, but what's the kinetic energy of an object is 1/2 mv squared. Since we're doing twiddles, forget the half. Doesn't matter. It's mv squared. And what's the energy of all the air? Well, the air moves too, so it's going to be kinetic. It's going to be mass of the air times the velocity it moves at. And what's the velocity the air moves out? If it's got to move out of the way and the thing's going velocity v, the air's got to move velocity v. So the v's cancel. And then we can twiddle our way to understanding that the contribution of air resistance as a sort of efficiency, what fraction of my energy gets burned into air resistance, is by twiddle analysis, the ratio of the mass of the air displaced by the mass of the object. And this is nice because this is actually something that we can understand, and it tells us how things vary, and it allows us to kind of go about our sense in the world, and we can easily estimate whether or not air resistance is important for real life phenomena. Like, let's say you're driving down the highway in your car. Does air resistance matter? Well, we can work it out. How much air are you pushing out of what's the mass of the air you push out of the way with your car compared to the mass of your car? You're driving down the highway. Density of air is 1 kilogram per meter squared. Your car is like 2 meters by 1/2 meter, or 2 meters, whatever. And let's say you drive like 10 kilometers because you're going between exits. How much does your car weigh? 1,000, like a ton, a metric ton. Divide all this thing out, you get a factor of 30. 30 is pretty far from 1, right? So you are pushing 30 times when you drive down the highway from one exit to another. The mass of all of the air in the tube that you kind of extrude is 30 times the weight of the mass of your car. So yeah, air resistance matters because your car is pushing 30 times its own mass out of the way. And that dimensionless number 30 is like unambiguously greater than 1. What about if I'm driving in the city? If I'm driving in the city, I stop at a light, I go to the next light. Now the distance changes. 10 kilometers, I might only go 100 meters, right? As I go a block from one stoplight to the next. So because we did the twiddle analysis, because we thought about what was going on, we also have a sense of the scales of the things involved and how things vary. If the distance goes down by a factor of 100, so does this ratio, and this ratio of mass displaced goes from 30 to 0.3. And now air resistance, I mean, 30% effect is not a nothing. I probably shouldn't ignore it, but it's also not the dominant effect. The thing that how fast I go or how much energy my car uses in driving from block to block isn't dominated by air resistance. But
So can we invert the 30 and say the mass of the car doesn't matter?
yeah, in the sense that I think it's right to leading order, to within about 3%. The mass of the car doesn't matter for figuring out how much fuel your car uses as it drives down the highway. And that's true. But it does matter when you're trying to go south, because the fuel in your car goes into pushing the car. As you're going down the highway, it's all going into pushing air. It doesn't matter how much your car weighs. All right, let's go back. Oh, so this was just another example of twiddle analysis. Let's say you don't know what the density of air is. I mean, that's the kind of thing you can look up, but it's also the kind of thing to gain some intuition for. We could do twiddle analysis for that itself. So how could we, if we don't know what the density of air is, how might we reason about it? Well, we could reason, we're talking about air resistance. We could look at powers, right? I could compare I have. I know how fast I can ride a bike, roughly, and I know how fast I can swim. And those are different. And what's different about them? In one case, I'm pushing air out of the way. In the other case, I'm pushing water out of the way. How hard do I have to work? How much power do I have to do? Power is a force times the velocity. You might not know that, but hopefully you do know that power is like a fuel use. It's an energy use. It's dE dt. If we're doing twiddle analysis, a derivative, the change in energy divided by a change in time is just a characteristic energy divided by a characteristic time. We go back, the energy was rho a v squared, d divided by time. D divided by time is another velocity. So the power used to move through a material due to its resistance is like rho a v cubed. And now I can compare water to air. The density of air to the density of water, because the powers are about the same, I get just as sweaty. Well, I don't get sweaty in water, but I work just as hard riding a bike, pushing through air as I do going swimming. And so my power is going to be the same. If I equate rho a v cubed to rho, differences, the rho's are different, the v's are different, then I discover that the ratio of the densities, the air to water, should be the ratio of the velocities cubed. I can probably swim at about 1 meter per second, and I can bike at about 10. 10x difference in the velocities when I'm doing the same power means that the density of air is 1,000th the density of water. And that's something I do remember. I know that water is 1 gram per centimeter cubed. So maybe if I didn't remember how much water air is, I could twiddle my way to it anyway. Okay, the next neat thing is tell us whether or not we should worry. And so it also tells us whether or not we should worry about different like branches of physics. So let's say we worry, do I have to worry about special relativity when I drop my racquetball? Well, we need a dimensionless constant that involves the physics. Special relativity is all about relativity, the speed of light. So all I need is a dimensionless constant that involves the speed of light. I need to get rid of the speed of light, so I need to compare it to a characteristic velocity in my problem. And for dropping the racquetball, we said it goes about meters per second. Speed of light's 3 by 10 to the 8. This dimensionless ratio is 10 to the minus 8. So this is just telling me, again, not knowing anything and not actually working out the relativistic equations. How much is relativity going to affect the speed of my ball when I drop it in my room? About a part in 10 to the 8. I really don't care about that. And I know that I shouldn't care about that because I can work out how much I should care. Let's say I worry about thermal fluctuations. Again, I just need to I need a physics constant having to do with thermal stuff, KB, Boltzmann's constant, and I need to kind of get rid of that. So I need to compare it to a characteristic energy in my equation. For my racquetball, it's like gravitational energy, mgh. Throw in the numbers, I get 10 to the minus 20. I super don't have to worry about thermal fluctuations when I drop my racquetball because it only matters a part in 10 to the 20. Do I have to worry about quantum mechanics? Well, what's quantum mechanics? It has to do with h-bar. So I need to get rid of h-bar. H-bar is an action, so I need a characteristic energy and time scale. For my racquetball, that gives me a dimensionless factor of 10 to the minus 34. I super duper don't have to worry about quantum effects when I drop the ball. I don't have to worry because this dimensionless constant is 10 to the minus 34, right? We do our Taylor expansion. It's only going to affect the answer to a part in 10 to the minus 34, maybe times a dimensionless constant. I don't care how big your dimensionless constant is. If it's only affecting the fractional answer to a part in 10 to the minus 34, I do not care one lick. Do I have to worry about what the phase of the moon is when I drop my racquetball? I just need to, again, come up with like a dimensionless constant that equates like what effect the moon has. So what does the moon have? It causes a force that's like mass and distance to the moon squared. I need to cancel that with something relevant. Let's compare it to the Earth. In this case, I get 10 to the minus 6. So Moon affects the drop of my ball to a part in a million. And that's the neat thing, is like this dimensional analysis, even if you don't use it to kind of get the exact formulas, it gives you can think about it, and it helps you understand when things aren't important. And that's maybe the more important thing. Let's go back to our bomb. We came up with dimensional analysis. We just got this like seemingly random thing. How do we do twiddle analysis? How do we make sense of it? Story. Story is the bomb exploded and it like had a bunch of energy, and that energy gets released. Where does the energy go? It goes into moving the air, right? This is a fireball. So the energy goes into the kinetic energy of the air. Kinetic energy of the air goes like 1/2 mv squared. Forget the half because we're doing twiddles. And we know that 1/2 mv squared, the mass of the air, if this is a fireball of size r, goes like rho r to the cubed times v squared. What's v? V is the velocity this thing is moving at. That's dr dt. The thing is spreading dr dt. Twiddle analysis tells us that dr dt is r over t. Stick this in this, and you get the thing that we saw. And now this makes sense. Why was this r to the 5th power? Because the energy goes into the air, there's r cubed amount of air, and as it spreads, that gives us another factor of r squared because of the velocity squared. We can make sense of how the thing scales. We understand the story. Okay, I'm running out of time. I wanted to, okay. I should probably stop, and we'll talk about all this stuff next week. This is probably a good place to stop. But, okay, I also need everybody's help. So I created a problem set, and you can kind of take a look at it. And I'd like people to kind of take a look at it. I also want people's help for what we should talk about next week. So I already have some things that I wanted to talk about. Basically, here are the options. I could talk about other sort of like meta strategies for optimization, things like scaling and divide and conquer and like gut checks and estimating intervals. And I can talk about all that stuff. I'd also hope to just kind of like work through a bunch of interesting problems having to do with maybe like, the climate of the earth and, cooking a turkey or things like that. And I guess what I want is some kind of feedback. Would you guys rather see sort of meta strategy type stuff, or would you rather just see like cool problems worked out? And the other thing that I need feedback in is how much physics are you guys comfortable with? Like, was this already sort of stretching things, saying things that like energy goes like 1/2 mv squared? Is that too much? Or can I kind of like do things at that level next week? And please let me know. And thank you for your time so far, I guess. And yeah, join me next week and we'll